Hey, hello everyone. Today, Ulrich Bauer is joining us, so thank you very much. From the Technical University of Munich, and as the title says, he's going to tell us about persistent homology and maybe applications to data. That's okay. Please take it away.
Okay, yeah, thanks very much. Thank you for the introduction. It's great to join this great seminar covering many topics related to topology. We heard you're this year focusing on TDA and higher categories. My talk will be about TDA or applied topology, and I want to give an overview of topics that showed up in my research, and they are often connected with geometry, like the data that we are trying to analyze is geometric, and somehow the data analysis is actually happening somewhere between geometry and topology. And persistent homology is the main mathematical tool that we use to study topology from data sets. And maybe as a first motivation, I want to explain briefly why we look at persistent homology and not just the standard concepts from homology that you know from algebraic topology. You may have at some point you may have found yourself wanting to explain to a non-topologist what you're doing, and you may have talked about this. But sorry, can you see the slides? I'm not sure if they are updated. Is this still the first slide showing?
The slide is also kind of behind you.
Yeah,
Yes,
yeah, that's okay. But I mean, is it updated? Do you see the title, or is the?
It's the title, the first slide. That's what we see.
Okay, so somehow then the. Oh, okay. Now it seems to work. Yeah, it's just okay. I mean, you may have found yourself bringing up this analogy when explaining what a topologist is doing, and you may have heard people say a topologist is the person who can't tell the difference between a donut and a coffee cup. Of course, that's a wild analogy, and it's not very accurate, but in some sense, it captures one aspect of what topologists are doing. But I mean, one way in which it doesn't quite capture what topology does is if you just zoom in more closely and you see what the donut and the shape of the donut at a smaller scale actually exhibits a lot more complicated topological structure than just a solid torus. So it's actually not quite true that the donut and the coffee cup are homeomorphic. It's just a matter of scale. And like if you squint your eyes, maybe they look homeomorphic, but if you look more closely, then both the donut has a kind of foam structure, but also the coffee cup will have a porous structure. And these porous structures will be very different. And in a sense, this already highlights one reason to look into persistent homology. When looking at geometric data sets, you actually want to somehow look at topology at multiple scales. And at the smallest scale, any real world shape would be maybe consisting of atoms. And if you look at the atoms individually, they would actually appear as a discrete point set. So that's also not what you want to capture. But somehow the initial motivation for the development of persistent homology in applied topology came from this project, the biogeometry project that Herbert Ilsbrunner was involved in the 90s. And they studied biological molecules like this one here. This is gramicidin, which is a very simple antibiotic. And the function of this antibiotic is very closely related to its geometry. If you turn it around a little bit, you see that this is a molecule that has a hole inside. And actually, it functions as a very simple ion channel. It attaches to a cell membrane of the bacterium that you try to kill. And then the ions can pass freely from the interior of the cell to the outside, and if there's a difference in the how many ions are present in the within the cell as opposed to outside of the cell, then this can eventually kill the cell. This is actually how this molecule functions as an antibiotic. And so it punches a hole in the cell membrane. So really here the geometry and the topological function of this molecule is very important. But if you want to study this shape, you actually notice it's not so easy to actually capture the single tunnel that this molecule is formed, because that's also one example where when you turn around this shape, you'll see that on top of this tunnel that you see here, there's also a lot of very small tiny holes that are in a sense the discretization artifacts of this simple model of a molecule and this ball model that is kind of a union of balls built around one ball centered around each atom in the molecule. So this simple model is a way of assigning a shape to a geometric point set. Here you see kind of a 2D simplistic example, and we have a bunch of points, a finite set of points in the plane, and you can think of this as a topological space, but it would be discrete. So topologically, it's not very interesting, but you can also already recognize this set of points seems to resemble an annulus, and one way to get a precise a way of arguing about the shape of this point cloud is to simply, as before, take unions of balls. And as you thicken these radii, you will get different shapes. And at this scale here, you see you have interesting topology. You don't really have the big hole in the middle hasn't formed yet, but instead some small holes have formed here. And these small holes, these are the discretization artifacts, if you want. So this is not really what you're interested in. But if you thicken a little bit further, then the small holes disappear and instead a big one appears. And that one is longer lived. So and the lifespan also of these features across the filtration. And when we talk about the lifespan of a homological feature, we need to make use of the induced maps in homology that are induced by the inclusion maps. And using this, we can actually argue that there's some short-lived holes that we have seen initially, and then there's one big long-lived hole that is only filled in at a rather large radius, at a large scale here. One thing to mention here, you see more than just a union of balls in this picture. You also see a simplicial complex on top of it. And that simplicial complex is what I'm going to talk about next. This is a geometric complex called the Delaunay complex. It's a subcomplex of the Delaunay triangulation of the point set. And that is guaranteed to capture the homotopy type of the union of balls. So that's the simplicial complex that we actually work with on a computer that captures the shape given by the union of balls. So that's one instance of a nerve construction, maybe the simplest nerve construction that is also often used in TDA, although it's more used for theoretical arguments because it's a very elementary construction. It's often called the Čech complex. We start with a point set as before, and we look at the union of balls of a fixed radius centered at each of the points. And then whenever we have a pairwise intersection of two such balls, we have a simplex, a one simplex. If we have a triple intersection, these three balls have a non-empty intersection, so they form a two simplex, and the resulting complex, the Čech complex, is the nerve of this union of balls. So this is a well-known, commonly used construction in topology and in category theory, where a variation of this idea appears. And in this setting, we simply given a cover of a space. In our case, this is the union of balls, and the cover is formed by the balls themselves. And the nerve simply records the intersection patterns of these balls. So whenever we are indexing the balls by some finite set capital I here, and all the subsets of this indexing set whose corresponding balls have a non-empty intersection, give rise to a simplex. This is a simplicial complex. And one reason why people are interested in these constructions, it gives under certain assumptions on the cover that are often called good cover, we are guaranteed that the nerve is actually homotopy equivalent to X. People have looked at quite a few variants of this theorem. So good cover here can actually mean various things. Maybe the most common example would be that we have an open and numerable cover. So we have partition of unity subordinate to this cover. And we also want to assume that the cover elements, as well as all the non-empty intersections of multiple cover elements, are contractible subsets of the space X. So that's one setting in which you can prove this conclusion of the Nerf theorem. Another setting, which is genuinely different and requires slightly different arguments, is if you work with a closed cover, and you can replace or strengthen the assumptions of contractibility to be convex subsets. So closed convex finite covers are what we are commonly interested in. And we are also interested in applying this Nerf theorem not just to a single space in a single cover, but we are working with filtrations. We always, because we want to study the geometry at multiple scales, we look at filtered complexes resulting from filtered spaces. And we want to understand how the topology changes across the filtration. So the fact that this construction is in some sense, and the homotopy equivalence is in some sense compatible with the filtration is important to us. And that's actually an aspect that has not been considered in the early versions of the Nerf theorem. The functoriality or the naturality of the homotopy equivalences is not is only something that people only later on have found interesting. And so we actually couldn't find a good reference that fully treats the case that we are commonly using in TDA, the case of closed and convex covers. And we also found that often people like to cite this Nerf theorem, but it is very easy to miscite it in a way where the assumptions are not exactly matched. So it's actually quite common if you find references to the Nerf theorem in the literature, that it is used and is stated in a way that is not exactly matching what people have proven in the literature. We found it might be valuable to have a survey on the different versions of the Nerf theorem, and especially in light of the applications to the TDA. So there's a recent survey paper that covers all kinds of different variants on the assumptions on the cover, and also the revisiting the theorem in light of the functoriality that's important for us when applying this to filtered spaces. And one case that's particularly important, as I said, is closed convex covers. And this is a variant of the Nerf construction that we have seen for the Čech complex. We want to apply this to the Delaunay triangulation, which itself can be defined as a Nerf. Namely, that's the Nerf of the Voronoi domains. So we partition here we see a point cloud in Euclidean space, in two-dimensional Euclidean space, which can be partitioned into its Voronoi cells, or we can cover them with closed Voronoi cells. A Voronoi cell is the set of all points that are closest to one of the points in my point cloud than to any of the other points. So here is a one point highlighted, and together with its Voronoi domain, which is the set of its nearest neighbors within Euclidean space. All the points that are closer to this, all the points in two-dimensional space that are closer to this data point than to any other data point. And the Delaunay triangulation can be thought of as simply a Nerf of this cover of Euclidean space by closed Voronoi cells. So whenever two Voronoi cells are adjacent, so they have an intersection, even though this is just a one-dimensional line segment, but this intersection will cover that they will show that these two are adjacent, and we will form an edge. And then we also have triple intersections, which are then just zero-dimensional, and these will be recorded by triangles. And if the point set is in general position, we will not have any more than 3 Voronoi domains meeting. And you can show that the resulting Nerf is actually a triangulation of the convex hull. And this is a construction that's commonly used in applied topology. And in particular, so this is classical construction from computational geometry. And in applied topology, we often kind of combine the idea of Čech complexes and Delaunay triangulation. which we call Delaunay complexes, or also sometimes alpha shapes. That was the original name by Edelsbrunner and Seidel when this idea was introduced in the 80s. And alpha, by the way, just stands for the scale parameter. So alpha is the radius of the pulse here. So the construction here combines the two ideas, the Čech complex, which is formed by closed balls, and the Delaunay complex, which is formed by Voronoi domains. And we simply take the intersection of two. So for each data point here, we show the intersection of the Voronoi domain with a closed ball. So it's a clip ball. And we can again form the nerve construction. So these clip balls will again cover the union of balls, but they will cover them in a more efficient way. We try to minimize the overlap. And as a result, we get a smaller but still homotopy equivalent complex. And that's some construction that is very useful in practice. These Delaunay filtrations, again, we can filter by modifying the radius of the balls. And this gives us a very powerful computational tool that can easily handle millions of points with current software. You may not be entirely happy with the shape of this simplicial complex. If you think about this cloud-shaped set of points, you may think that this triangle that's highlighted in yellow here is unnecessary. And in fact, there's a way to collapse away this triangle in a way that's also a homotopy equivalence. This was just an elementary collapse. And indeed, there's a principled way of carrying out such collapses to start with a Delaunay complex and replace it by an even smaller homotopy equivalent complex. And this construction is called the wrap complex. In order to be able to talk about what the wrap complex is, it's useful to introduce a language that is able to encode simplicial collapses. And that language has been developed in the mid-90s by Robin Foreman under the name of discrete Morse theory. So the idea was that a large part of classical Morse theory, the theory of critical points of a smooth function on a manifold, actually has a combinatorial essence. And discrete Morse theory extracts just this combinatorial essence. So the setting here is maybe visualized. I'm going to introduce this just by an example without giving the detailed definitions, to just give you a flavor of what this looks like. Here you see a simplicial complex. You see some numbers. So this is supposed to indicate a function on the simplices of the complex. And you also see some arrows. And the arrows indicate what's called a discrete gradient field. So they give, there's always an arrow from a simplex to another coface of codimension 1. And these two simplices, all the simplices with indicated by an arrow, share the same function value. So we have function values from 1 to 6. Function value 1 and 6 appear only for a single simplex. So these are the critical points of the function. And everything else is appearing in pairs. And so these are the regular simplices. And the idea of Morse theory is, if you want to describe the homotopy type of the space using the function, only the critical points really play a role. And so in this sense here, the main theorem states, maybe I should say something about the function values before. The function is supposed to be monotonic. So larger, if I have a simplex and I have a face of that simplex, the face has a function value less or equal to the simplex itself. So the function is a monotonic poset map from the face poset to the real values. So it's a monotonic function. That's the one condition. And the second condition is that the function partitions the set of simplices into either singletons, like 1 and 6 here, or pairs, like the other function values 2, 3, 4, 5, which appear as two simplices of codimension 1. And one is the face of the other. So these are two conditions: a monotonic function that partitions the simplices into singletons and pairs. And the main theorem of discrete Morse theory says, if I have such a function, a discrete Morse function, then the domain of that function is homotopy equivalent to a space formed just from the critical simplices of the function. So in this example here, you see only 1 and 6 are critical. Those are the cells that are sufficient to give the homotopy type of the complex. And discrete Morse functions are useful for encoding simplicial collapses. So here's an example. We take this the levels for the functions simplices with function value up to 5. And you observe that we want to show that this is the same homotopy type as if you go only up to level 2. And this is certified by the fact that between 2 and 5, there's only regular values. All the simplices with these values appear only in pairs. And you can see really the arrows indicate the collapses, and collapsing in an appropriate order from the 5 level set to the 2 sublevel set does not change the homotopy type. And this is very important. This is a powerful language to express homotopy types and collapses of homotopy types. This is not quite the situation that we need in when talking about Delaunay complexes, for example, but there's a slight modification of the setting that still allows us to argue in the same way. Instead of just requiring singletons and pairs, here we look at larger clusters. So the generalized assumption is that the function values partition the set of simplices into intervals in the phase poset. A singleton is clearly an interval. An interval in the poset is given by a common lower bound and an upper bound. So here in this example, all the simplices that share this green vertex and are contained in this green triangle, these are the lower and upper bounds. And the set of all such simplices forms an interval in the phase poset. And we can always refine such intervals into pairs, and so this generalized setting still makes all the results of Morse theory, discrete Morse theory, applicable. And here's one result that can be stated using this language: the Čech complexes that we have seen before, and also the Delaunay complexes, and then this third class that I'll introduce in a moment, the RAP complex, they're all homotopy equivalent, and this is encoded in a single gradient that records both the relationships across different scales, as well as the relationships between the different 3 types of filtration. So the whole situation and these different constructions can be expressed, the common structure is expressed in a single discrete gradient field. Let me just say something more now about the third construction, which seems to be the nicest one here, the RAP complex. Here is an example of a applied to a...
Before you move on, can I ask you a question about generalized discrete Morse function? So as I remember, in the normal Morse functions, you had this condition of no loops with the pairs, right? So in the discrete Morse one, where you take the posets as intervals, is there a similar condition?
Yeah, there's a similar condition. The condition that you have no loops is basically given already by the assumption that the function is monotonic with respect to the phase order. And that excludes the existence of loops. So I kind of made this assumption implicit in the definition, right? So, but you can also rephrase it in a more explicit way that talks about no loops.
And in the generalized discrete Morse, when you number the intervals, that condition becomes just the same condition.
It's a very similar condition. So you can say if I have a monotonic function on the simplicial complexes that partitions your complex into intervals in the phase poset, then this is a generalized discrete Morse function.
And that works in the same way.
Yeah. So this is just a small modification, and we'll see why we need this modification, because that's exactly the nature of the functions that give rise to Čech and Delaunay filtrations. They're given as functions. The Čech complex is for the Čech complex, it's the function that assigns to a simplex the radius of the smallest enclosing sphere, and for the Delaunay complexes, it's the radius of the smallest empty circumsphere. Empty means empty of the other data points. So and so that's the natural setting that we see here. This is also why it took some time to connect discrete Morse theory and Delaunay and Čech complexes, because it wasn't immediately applicable to the theory that Foreman had suggested. But having this theory, you can also re-express the RAP complex, which has been introduced around the same time as the discrete Morse theory, but it took several years longer to use that language to unify the two theories in a sense. And so this has been used successfully in surface reconstruction software. So Geomagic is actually a company founded by Edelsbrunner. And here you see an example, like this is a famous point cloud, the Stanford bunny that's often used in computer graphics. And what you see here is really the RAP complex of that point cloud. So the idea is you simply take the smallest subcomplex of the Delaunay complex that is still compatible with the Delaunay gradient. So in other words, so you take the smallest subcomplex that contains all the critical simplices and is a union of the Delaunay intervals. And what that means, if I start with a critical gradient and I'm including all its faces to make it a subcomplex, but at the same time I also have to include the entire interval of that face. So and then I go on. So I have more simplices, and I also again have to include their boundaries together with all the simplices in the same intervals. And so what happens if I continue this game? I start with a critical simplex and I kind of flow downward the gradient until I have a subcomplex formed by that critical simplex and compatible with the gradient. And I do this for every critical simplex below my threshold R here in this definition. And I take the union of all those complexes generated by the critical points, and that's the RAP complex. So it's the smallest complex that is guaranteed to be homotopy equivalent to the Delaunay complex by compatibility with this gradient. Here's an example. This is the Delaunay complex. You see there's some unpleasant artifacts. The bunny has a collar, and the RAP complex looks much better, much cleaner reconstruction of the shape. There's some more recent development that actually uses algebraic methods, so homology computation in a sense, to reconstruct a surface, and we will see that this can be related to the RAP complex in a certain way. So let me show you an animation. Here's my data set. Now this is a 2D example first. You see the Delaunay triangulation of this data set. Here, the critical simplices of the Morse function are highlighted. Here you see the Delaunay complex. There are some artifacts. And here you see the RAP complex. And you see there's still some unpleasant artifacts, even in the RAP complex. And we'll see now how to get rid of those as well. What we'll do is we start with a single triangle. And that will be a critical triangle. And it will be the one that kills the feature in homology in its filtration with the longest lifespan. So the largest ratio of when the scale at which the feature appears to when it disappears. And let me just run the animation. So what we're doing is we'll start with the boundary of this triangle and we'll replace it by homologous triangles that have shorter edges. And so what you see here, what's happening is actually the algebraic computation of the homology class. Actually, this is a computation that applies to the entire filtration. So it's computing persistent homology. We'll get to this in a moment. And the final result that you see here is a very nice boundary whose boundary edges are very short. They're kind of minimal in some sense. And so this is the proposed method for reconstructing the curve here. And there's also, you can do this in 3D. You start with a single tetrahedron, and then you try to run the homology computation, which actually tries to replace this boundary of the tetrahedron by another boundary with smaller triangles. And as you see, what happens in this computation is the tetrahedron blows up, it fills the entire shape, and the final construction is a very nice reconstruction of the surface. So this seems to be a method that works very well, and interestingly, we're doing nothing too special here. What the computation that you see is pretty much what everyone has been doing for a long time when computing the homology of the entire filtration. So oh, this is just one more.
Can I ask one more question? If that's okay.
Yes.
In the previous animation with just the 2D dots, you started with a triangle inside.
Yeah.
But it never sort of flipped to the outside.
Yeah,
what
and it's
was
not
the reason for that?
What's that?
What was the reason for that? Like
the reason is that, so what the computation does is it starts with that triangle, that initial triangle, and it tries to replace it with another boundary. So it replaces the boundary of that triangle with another boundary that's in the same homology class in the filtration right before that triangle itself enters. So it's a homologous boundary that tries to minimize the length of the edges in the boundary. And what you saw is like it does not never flip to the outside because that would not decrease the length of the boundary edges. And so in a sense, the goal here is to find that earliest representative of the homology class in the filtration, and we're trying to represent this as early as possible and with as small simplices as possible. And the result is what you see here.
But in the earlier pictures, you have these triangles on the corner. So in the length of those will be higher. Is that why they stay there in the Delaunay complex? So what is the new idea here? Like you change your numbers to make it a Morse complex and then you contract it, or
no. So
it works better. Yeah.
So this is well, this is based on a given function. We're not modifying the function, but now we're looking at a homology class in the filtration. Mm-hmm. So we go in the filtration up to the step right before the maybe I'll go back. Oh, sorry, there's something. Just a second. Yeah, I mean, right before this first tetrahedron in this example enters. So before that step, there's still a hole in the middle of the bunny. Mm-hmm. And so I'm trying to find a homology class, a cycle in the homology class that's homologous to this boundary of a tetrahedron. I know this is a non-trivial class, and what this computation does is it tries to change within the homology class and find earlier and earlier cycles in the same homology class. And what I reach at the end is the earliest cycle and the lexicographically smallest representative within that homology class. And that's what I'm going for. And the claim is we can actually relate this particular representative of the homology class to the wrap complex. We can actually prove here some more examples applying this to data sets. And you can actually prove that the cycle that we obtain this way, so it's going to be a lexicographically minimal cycle. If I equip the set of cycles with a lexicographic order based on the filtration order of the simplices. And then we're guaranteed that this minimal cycle that we're computing is actually supported on the wrap complex. But already in this example, we see the support of the cycle is actually a bit smaller than the wrap complex. And this is what we're going for. We try to remove the remaining artifacts. And the good thing about this method, it guarantees us to return a boundary of a 3 chain here. So this is something that people in computational geometry always find very desirable. This is what they call a watertight surface reconstruction, that the result is actually a boundary of something solid. Okay, so this is just to illustrate that it very interestingly, like a purely algebraic method, when we apply it to geometric data, it seems to provide us with geometric results that can actually be related very nicely to previous methods for shape reconstruction. Let's talk more about the idea of looking at homology of filtrations, which is in a sense an old topic that has received a lot of new interest in the context of applied topology. Persistent homology just means we're looking at a filtration of simplicial complexes, and we are interested in the history of the homology groups. For good reasons, we're doing this with homology with coefficients in a field so that we get vector spaces, because then what we're dealing with is a one parameter family of vector spaces, and we have the machinery of a representation theory to study such objects. So here is one description of the entire history of the homology groups. Here, let's just say we're interested in homology in degree 1. So we are looking at these one-dimensional cycles. And what you see here, down here, is basically a collection of intervals just arranged vertically by their length. And this encodes the lifespan of all the features in homology that appear across these scales. So let me explain what this means. If I choose a scale, let's choose 0.1, and I look at all the intervals in this, what we call a persistence barcode. It's a list of lifespans. So and I have 5 intervals that contain this value 0.1. And this indicates that at the scale 0.1 in the filtration, there were the Betti number was 5, and there were actually 5 cycles that generate a basis for the homology attached, one cycle attached to each of these intervals in the persistence barcode. And what this allows us is to read off the Betti numbers at each scale in the filtration, but even more and much more important for us is to also read off the ranks of the maps between 2 different scales. Simple example here is the scales 0.2 and 0.4. You can read off from this diagram here that the rank the map in homology between these 2 scales has rank 1, because there's exactly one interval that contains both values. And here's the corresponding cycle. You can see it's the same cycle in both complexes. That's one cycle attached to each interval. And so we can read off the entire information, all the dimensions and all the ranks in homology at once from this diagram. So formally speaking, what this persistence diagram shows is really the structure of this one parameter family of filtrations in terms of a direct sum decomposition. So what we are starting with is a filtration, so a family of topological spaces indexed over the reals. So we view this as a functor from the poset of the reals to topological spaces, and all the structure maps in this functor are inclusion maps. And we can post-compose this with another functor, with a homology functor. And this gives us, this sends us into vector spaces because we work with coefficients in a field. And so the composite, so first the filtration, then homology, this gives us the persistent homology. And this is the type of this object is what we call a persistence module, a functor from the reals to vector spaces. And so that's an object, that's the type of objects that representation theory studies, functors from anything into vector spaces. And representation theory would consider this as a complicated object and try to do a direct sum decomposition. And we want to study algebraic objects by decomposing them into the indecomposable parts. And that's really what the persistence barcode expresses. So one theorem that has been shown in the greatest level of generality by Crowley-Bovey, who is a representation theorist. And he showed that any persistence module, if we are guaranteed to have finite dimensional vector spaces, always decomposes into indecomposable summands of this very simple form. We have an interval of real numbers across which we have the field connected by isomorphisms, and then outside of that interval we are 0. And every persistence module is a direct sum of such interval modules. And the persistence barcode is simply a description of the collection of these intervals. So the persistence barcode describes the isomorphism type of the persistence module, and that's why we are making use of the existence of this simple description in persistent homology. And it's very unusual because even just going into 2 parameters, you entirely lose this kind of simplicity in the structure. We don't have anything like this for 2 parameters. 2 parameters is something that practitioners would like to work with a lot. But so if you have, in general, in the abstract setting, you have a grid-shaped diagram of this form. So you have horizontal and vertical maps and vector spaces, finite dimensional vector spaces everywhere. Then representation theorists know that, well, depending on how large this grid is, there are 3 cases. The first one, if, and you can distinguish them simply by counting the number of squares that this grid describes. If we have less than 4 squares, we are still of finite type. We have a finite list of indecomposables. So that would include the, if you would index over the natural numbers, it would include the 1 parameter case where you have 0 squares. If you have exactly 4 squares, so that means if the grid is 3 by 3 vertices or 2 by 5 vertices, then we are Payne type. We have for every list of dimensions, we have 1 parameter families of indecomposables. But then there's a third class. As soon as we have more than 5 squares in the grid, we are wild type. So the representations are so complicated that any other module category of finite dimensional algebras would embed in this already. So very quickly, the situation is not cannot be classified in terms of indecomposables anymore. And so that poses a big problem for us when trying to study 2 parameter persistence. The indecomposables seem to be of little use. And the problem is actually a very practical one. I mean, here's one example illustration why we would be interested in. The problem would be to count the clouds here in this picture. And well, you will have a hard time saying how many clouds there are because the problem is a bit ill-posed. And the trouble is, in a sense, maybe here's again a sketch using only points. The question is this actually 1 or 2 clouds? Is this 1 or 2 clusters where I'm sampling from? And again, it depends on not just the scale, but it also depends on the density of the points. And so you actually want, in order to answer the question how many clusters are used to generate this data set, you actually want to study a 2-parameter filtration where the first parameter is a geometric scale and the second parameter would be some kind of density estimate. So if you just look at union of balls, you very quickly merge the 2 clusters. But if you instead look at a filtration where you only filter out the points that seem to have higher density and then take unions of balls of these 2, you recognize that there seem to be 2 clusters in this picture. So this is an approach that is actually used in practice a lot in clustering methods. You want to say the number here is 2 and not 1. But in order to do this, you're actually dealing with 2 parameters. And you are in a setting where homology and the persistent homology over these 2 parameters gets very complicated. And that is even true if we're just looking at zeroth homology. So we were wondering if there's something in this setting that could simplify our life. And the observation here was that we actually have 2 parameters, but one, namely the scale parameter, only gives us surjective maps for the simple reason in zeroth homology, if I increase the geometric scale, I will not add new points, but I will only merge existing points. So the scale parameter only merges connected components. And that means in zeroth homology, in the direction of the scale parameter, we have only surjective maps. So we don't have arbitrary grid-shaped diagrams, but we have a very special kind, namely epimorphisms in the horizontal direction and arbitrary maps in the vertical direction. And our question was, well, this means we can simply argue that the representation theory is complicated. But we actually found that the situation is much is different than from the general picture, but not by much. So we have that the representation theory of m by n grids with this particular property that we see in zeroth homology is actually the same as if we remove one row from this grid. If we have one fewer rows in the diagram, and the representation theory we get from such grids is the same as the one that we see here. So in particular, if we start with 2 rows with this property, we are in finite type setting, but everything else we're quickly in wild type. So in a sense, this is bad news. And it is also related to another topic that I think is very important in persistent homology, that's stability of persistence barcodes. And again, there's a big question about the stability in one parameter versus the non-existence of stability in 2 parameters. So let me explain what that means. In a sense, the barcode is a kind of structure theorem. It's a Kroll-Schmidt theorem saying that any persistence module has an essentially unique decomposition. And we have seen this in algebra in many instances where we can describe algebraic objects by a unique decomposition. Stability, in a sense, generalizes this to an approximate Kroll-Schmidt type theorem. That's one way to interpret it. It says if we have 2 similar inputs, then the decompositions are also similar. Like, as opposed to if we have 2 isomorphic inputs, then their decompositions will be the same. But here we have some kind of approximate version of that. So explicitly, this means in terms of data points, we have given 2 data points, 2 point sets shown in red and in blue here, and you see that they are nearby. You can recognize from this picture that they have small Hausdorff distance. And this fundamental theorem of stability of persistence barcode states if the Hausdorff distance of the 2 point sets is small, then also the distance of their persistence barcodes will be small. In the following sense, we can match up the intervals in the barcodes, like you see here, in a way that the matched intervals have similar endpoints. They will differ only by delta, if delta is bound on Hausdorff distance. And the unmatched ones have to be short. They have to be at length at most 2 delta. So we know similar inputs give similar barcodes in this sense. This is a fundamental statement that, in a sense, can be viewed as Lipschitz continuity of the map that sends a finite point set to its persistence barcode eventually. And if you look at this in the big picture, there's multiple steps that lead from a point cloud to its persistence barcode. The first step is we consider the distance function to that point cloud. So that's a function defined on the entire Euclidean space. And the union of balls of radius r is the sub-level set of that distance function at level r. So that forms from this function a filtration of topological spaces. Now, to this filtration, to the union of balls filtration, we apply the homology functor, and we get a persistence module, the persistent homology. And then we study its structure, and we obtain the persistence barcode. And stability really says in this entire pipeline, each of the 4 steps can be thought of as a one Lipschitz map between metric spaces. Here we have the Hausdorff distance between point clouds. Here we have the L infinity distance between 2 functions. And the last 3 stages here are all functors indexed by the real values, taking value in some category. And such functors have a common notion of distance that I will explore now. They are the notion is the interleaving distance. And let me just illustrate what the interleaving distance does on a simple example. By the way, before we go there, the first proof of stability went straight from a function to its barcode and showed that this step is stable. And later on, people found that actually the hard part in proving stability of persistence diagrams is really just the last step, going from a persistence module to its barcode. And I will sketch in a moment how exactly you can see that this is stable. so we need to have a notion of distance between persistence modules, between filtrations, and also between the barcodes, if you want. And that notion is the interleaving distance. It's motivated by the fact that if I start with the blue point cloud here, and then I have nearby the red point cloud appearing here, then the blue point cloud is a subset of the delta thickening of the red one. And delta is the Hausdorff distance between the 2 point clouds. And conversely, I mean, that delta thickening of the red point cloud is contained in the 2 delta thickening of the blue one. And you can go on and you can go back and forth between thickenings of red and blue, always increasing the threshold by delta. And this gives you a diagram that we call an interleaving. And in the setting of sub-level sets of functions, if we have 2 functions f and g, whose infimum is supremum distance is delta, and then we consider the sub-level sets of both functions, then they're also interleaved. So you can set up a diagram where the rows are the filtrations of both sub-level set functions, and then there's natural transformations shifting the degrees by delta that connect the 2, and combining these natural transformations gives you like they compose to the internal structure maps in both diagrams. So this entire diagram, the shoelace-shaped diagram that you see here, is a commutative diagram, extending the functors f and g, these filtrations of topological spaces, to a larger diagram. And now applying homology to this diagram still maintains the commutativity of the diagram. So, and this immediately gives us that from an interleaving of 2 filtrations of topological spaces, we obtain directly an interleaving of their persistent homology. And so this is the notion that we want to apply. And with this language, we can express what it means for the persistence barcodes to be stable on the algebraic level if we have 2 persistence modules that are delta interleaved, which is the case if we consider persistent homology of 2 point sets that are at Hausdorff distance delta. So then we have delta interleaved persistent homology, and algebraic stability says this is enough to show that also the barcodes admit this delta matching. So the same property as before, the endpoints are similar for matched intervals and close to each other for unmatched intervals. And well, what's behind this? A simple observation that actually now we're looking into the structure of submodules and quotients. So let's say we have 2 persistence modules, M and N. M is shown in blue and N is shown in yellow. And if I assume that yellow, the N is a quotient module of M, so this is just a quotient object. At each index, I have an epimorphism. And I have a natural transformation from M to N with this structure, then I am guaranteed that their barcodes will somehow look very similar. They will, the left endpoints will be aligned, and the right endpoints of the quotient will be shorter, will be earlier than the right endpoints of the original module M. So we get an injection from the barcode of the yellow of the quotient into the original module. And that's actually a functorial construction. And we have a dual statement for monomorphisms where instead of the left endpoint, the right endpoints are aligned. And now this is actually a very useful observation that quotients and sub-objects in the world of persistence modules have this similar structure, because now we can simply take an arbitrary morphism and we factor the morphism through its image. And now that image will be a sub-object of the domain and will be a quotient of the domain and a sub-object of the codomain. And for both, we have a matching of barcodes, and we can simply compose these 2 matchings, and that gives us a matching from the domain to the codomain. And now, as it turns out, if we are in the interleaving setting, this way of obtaining a matching actually matches up the intervals in a way that's compatible. One thing that should be noted here is this construction here is no longer functorial. It does not respect composition of morphisms. And another thing that's a bit mysterious about this construction is You may hope that this way you can actually decompose the entire morphism as a ladder-shaped diagram. And that's actually not the case because it's not possible in general. So in a sense, the induced matching that we obtain in this way is only approximation to actually decomposing the entire morphism. But it still does good enough of a job to guarantee that we obtain stability of persistence barcodes. So using this, we can actually assemble here as an illustration. We start, let's say we are given two persistence modules that are interleaved, and we're looking at the interleaving morphism F. And here's the image of that morphism. And then we're matching up the corresponding intervals through the image, through the barcode of the image. And now the statement is the following, or a theorem that implies that the statement of stability. If the kernel of this morphism has only short bars, and that's a property that's guaranteed in the setting of an interleaving. If I have an interleaving between two persistence modules, the kernel and the co-kernel both will have short bars. And the statement here is it's guaranteed that then the mismatch of the intervals in blue and yellow, so in the domain and in the image, will be small. So this can be actually expressed as a kind of kernel. This kernel of the induced matching psi f that you see here is simply this consists of the where it can be obtained by starting with the barcode of the domain M and removing for every interval in M the matched interval from the image and leaving only the part that is not appearing in the yellow interval. So you see there's a long interval in the barcode of M. It is matched to a yellow one, and what you see here in brown is the part of the long interval that has not been covered by the yellow matched interval. And the statement of the theorem then simply says if the kernel of F has short bars, then the same is true for the kernel of the induced matching. So even though the induced matching is not functorial, we have some kind of good properties with respect to preservation of shortness of kernels and dually for co-kernels. And that implies if I start with a delta interleaving of persistence modules, then I obtain a delta matching of the barcodes. Okay, so that's kind of a glimpse at what the machinery that's used to prove stability. This construction of induced matchings, by the way, is so explicit and so simple that we actually applied this also in a setting where we try to train a neural network in a machine learning setting to improve segmentation of medical images. And we use the induced matchings between an image that the neural network generates and the training image to train the network to segment in a topologically correct way. So some of this tool that we see here as a proof gadget could actually be also applied in a machine learning setting as a very efficient computational tool. Let me now switch to the indecomposables in a multi-parameter setting, where the situation is unfortunately very different. We have where we could decompose any persistence module over one parameter into very simple building blocks. If we have more than one parameter, we have this strange situation that almost every n parameter persistence module is indecomposable to begin with. So it can actually have very large pointwise dimensions, and we may not be able to break it apart in a sense. And this is a very, very different situation. So given an arbitrary persistence module may be coming from two parameter filtrations, it may decompose itself, but there's always an indecomposable one arbitrarily close in the interleaving distance. And then on the other hand, given an indecomposable one, any other persistence module nearby sufficiently close to this is maybe not indecomposable itself, but it can be written as a direct sum of an indecomposable one and a second summand, which is guaranteed to be small, have in a sense the algebraic analog of having short intervals in the barcode decomposition. So this can be stated in a different way as saying the indecomposables in multi-parameter persistence form a dense subset in the interleaving distance, and being indecomposable up to maybe very small summands in the interleaving distance, close to 0 in the interleaving distance, that's a generic property for any epsilon. So in a sense, we could get a lot of leverage in one parameter setting by viewing persistence modules in terms of their structure, but it's very difficult to say something about multi-parameter persistence modules using the same lens. I don't know how much, so I have 2 more topics that I could talk about, but I don't know how much time we still have. So we started a bit late.
Oh, yeah, we started a bit late. I think 5 or 10 minutes more or less, but you can have more minutes if you like. Like how long do you think those 2 parts are going to take?
Yeah, okay. I mean, so maybe the next thing is I might not get to everything, but the next topic is an interesting aspect of the origins of persistent homology, which actually dates back to the early 30s, actually. So there's a paper by Marston Morse. I mean, this appeared in late 30s, but it took Morse quite some time to develop this theory. And he, in this paper, which this paper has not been cited much. I mean, this is a screenshot from Google. It's already a few years old, but you can see that it was cited less than 10 times. The way I found about this was in this survey paper by Raoul Bott on Morse's mathematical heritage. And he explains in this paper a work that he describes as not easy reading and a tour de force by Morse. And so he says, rather than going into the technical details, let me explain what's happening. And then he shows this picture here, which is supposed to show a polygonal embedding of a circle. And you look at the height function. And then he says, well, at the level alpha, homology, homology in degree 0 is born. And then at the level beta, another connected component, another feature in degree 0 is born. And then lambda and gamma both change the homology again. Lambda closes a 0-dimensional cycle, while this mu here generates a 1-dimensional cycle. And he then also explains that, in a sense, the homology that's born at beta is killed by lambda. And so these are paired up. And that's actually exactly the observation that we explain now in persistent homology in terms of the decomposition. This is not how Morse thought about the setting. And so his language of talking about the phenomena of persistent homology in those works was rather complicated, and that's maybe why not a lot of people have picked it up. But there's the reason why he introduced these ideas was there was a famous problem that people looked into at the time, Plateau's problem of finding unstable minimal surfaces. So the idea was, this is sketched here. You see 2 minimal surfaces, smooth surfaces with vanishing mean curvature, and bounded by the same boundary curve. And the goal was to somehow show in this setting, you wanted to understand what possible minimal surfaces could exist. Douglas was awarded the first Fields Medal actually for describing minimal surfaces in terms of functionals defined only on the contour. And there was a lot of impetus, and people wanted to show the following statement, which was shown by Morse and Tompkins in 39, and then almost simultaneously by Schiffman using different methods. And so that's a theorem that was proven using ideas from persistent homology. So the statement is, if you have two minimal surfaces that are within the same connected component in the energy functional, and they're both actually minimizers, local minimizers of the energy of the surface energy, then there has to be a third one, which is a saddle point, right? So this is intuitively, if you have two local minima of a function, then there must be a saddle connecting the two minima. And this is happening in a very high dimensional function space here, where the minima are actually the minimal surfaces. So this is the theorem that people wanted to show, and to develop machinery for this, the authors, including Morse, developed that it's important to describe what people in persistence theory have later on found sorry, an important concept that's relaxing our finiteness condition. Instead of asking that the persistence modules are pointwise finite dimensional, as we have seen before, we only require that the ranks of maps between two vector spaces in the persistence module are finite. So we don't care about the dimensions at each index, but we only care about ranks of maps across different indices. And in this language, which is helpful because in this setting, you can actually still define a barcode. You can't say anything about the endpoints of the barcode anymore, but you still have a valid description of counting all the ranks between different indices. And Morse's main technical result was actually to show that the minimal surface functional has this property that it has Q-tame persistent homology. So going from one sublevel set of the energy functional to another, the induced map in homology will be finite. So this is maybe the first instance, and it's a very challenging because it's pushing the boundaries of what you would easily reach with basic machinery. So this, at a very early stage, people already saw a need for developing persistent homology in a very general setting. And then Morse's technical result could be stated as follows. If you're given a sublevel set filtration of a function whose sublevel sets are compact, and a condition that he calls weakly locally connected, then it's guaranteed to have Q-tame persistent homology. At this time, this was in the 30s. He actually used Vietoris homology. So interestingly, we have looked into this paper very closely, and at some point we found that the statement there's a gap in the proof, and the statement as stated by Morse is actually not correct. And you can actually cook up a simple counterexample by looking at the Hawaiian earring and constructing a function on that Hawaiian earring that actually shows that this statement is not satisfied. Fortunately, there is a fix, and we, together with Medina Madonis and Schmal, we could find a way of rephrasing the ideas of Morse in a modern framework that is more compatible with persistent homology, with a modern development, and we could actually regain kind of a fixed version, a corrected version of Morse's statement that can be used to address the questions raised by these minimal surface questions. Okay, I think that's maybe a good moment to end here. Thanks for your attention, and please, if you have any questions, feel free to ask.
Okay, thank you very much, Ulrich. Okay, any questions?
I have a question, but it's a little bit the earlier part. When you define the delta intertwined, you had maps between two different filtrations.
Yeah.
Generally, you can find such maps, but do you require something about these maps?
Yeah, so there's the green maps from the F filtration to the G filtration, and then there's the brown maps from G to F. And the entire diagram that you form in this way should be commutative.
I see.
So that means going from F to G to back to F should be the same map as the structure maps within the F filtration. So this should be thought of, a delta interleaving is an approximate isomorphism, right? It's an isomorphism up to a shift within the persistence modules. If you find a delta interleaving for delta equals 0, that's exactly an isomorphism. And so this is the sense in which we loosen the notion of isomorphism to something approximate.
But this will always be possible to find if you had two data sets that their Hausdorff distance is less than delta, then their Rips complex or
here the
complex
Delaunay or Czech complexes, right?
Always
exactly, because the reason is, maybe if we go back to this picture, if the Hausdorff distance is bounded by delta, then the distance functions are bounded by delta in the infinity norm. And then this means that the two filtrations are interleaved by the argument we have just seen. And so we go on in this. So we have a delta interleaving of filtrations. We directly get a delta interleaving of homology. And then the stability for persistence barcodes tells us we also get a delta matching of the barcodes, which is a variant of the interleaving.
And this delta distance for the barcodes you define, that when you match, the distance will be delta, and then unmatched to delta. Is it same as the bottleneck distance?
Yeah, it's also right. This is the bottleneck distance.
Is it exact same with just different phrasing, or? Yeah,
it's the same as and you can also, so it is exactly the bottleneck distance, and you can also think of it as an interleaving distance. So this is, I haven't mentioned this here, but you see, you can view the barcode as a functor from the reals to the matching category, which means the objects are sets and the morphisms are partial bijections. So or matchings as you use them in combinatorics. And you can actually show that if you interpret a barcode as such an object, then the bottleneck distance is exactly the interleaving distance.
Nice.
So it fits naturally in this picture. However, the passing from persistence modules to the barcode can be obtained by a functor, so you have to prove the stability in a different way.
Any other questions? I have a question about the tame version. So you're dropping the finiteness condition. Is that so the finiteness condition come from the finite simplicial complexes, right? Those are like, we're looking at point clouds that are essentially finite. And what is the motivation for the Q-tame version? Is it coming? Does it have any application, or is it just a gadget that's?
I think there's a very good reason also in the geometric setting. You can think, let's say you want to study compact metric spaces, and you can approximate any compact metric space by a finite one in a Gromov-Hausdorff distance. And so in a sense, what you can describe, if you take the closure now of all the finite point sets, you in the Hausdorff distance, you get the compact ones. And so this is at the limit of what we can actually handle with these finite methods. And now you can also easily see, because any finite metric space has a pointwise finite dimensional persistent homology, this implies, and it's any compact metric space is arbitrarily close to a finite one, we must have that the persistent homology of the compact metric spaces are Q-tame. So in the geometric setting, Q-tame persistent homology shows up very naturally as the class in which the compact metric spaces, the persistent homology of the compact metric spaces lives. So that's why we are, I guess that's the first instance why we in applied topology are interested in QTame. And then for a very different reason, maybe the same notion appears quite naturally in functional analysis as well. So, and I think in some sense, you can also argue this is the largest class of persistence modules that still can be studied with like through the lens of direct sum decompositions, where we're guaranteed to have a barcode and really can argue about the persistence module in terms of the barcode. So it is, I mean, it is beyond what we can express with any given data set, but it's really the limit of what we can do. And that's why we're interested in this.
Okay, thank you. Any other questions for Ulrich? Okay, if not, let's thank the speaker. Thank you very much.